Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. The supercomputer that is not parallel processing or computing many things at once is like a train without its locomotive. In the early 1980s, I discovered that it would be theoretically impossible to send emails back and forth through a new internet that is a new global network of commodity off-the-shelf processors. That is, commonly available processors derived from the same processor, same memory, and same board technologies that were used to power the personal computers of the 1980s. It was a paradigm shift because the new massively parallel processing supercomputer is several orders of magnitude more cost-effective than the prevailing vector processing supercomputer that was the fastest in the 1980s. I'm Philip Emeagwali. I'm the first person to ever discover the fastest computations across the slowest processors. I experimentally discovered how to use 64 binary thousand computer codes that executed floating point arithmetical operations that arose while solving the toughest problems in modern calculus. I experimentally discovered how to execute 64 binary thousand excruciatingly detailed general circulation models and how to execute those models to foresee otherwise unforeseeable global climate changes. I experimentally discovered how to execute those models and execute them as 64 binary thousand petroleum reservoir simulators. I experimentally discovered how to execute those reservoir simulators and execute them to recover otherwise unrecoverable crude oil and natural gas. I experimentally discovered how to execute computational aerodynamics codes and how to execute them to design the complex geometric configurations of aircrafts that will yield better fuel efficiency. I experimentally discovered how to execute them to simulate airflows across aircrafts that were not confined to the inside of a wind tunnel instead of simulating airflows across aircrafts that were confined inside a wind tunnel. I experimentally discovered how to use them as 64 binary thousand computational fluid dynamics codes and how to use those codes to hindcast the past motions or forecast the future motions of planetary fluids such as the Earth's oceans and atmosphere, as well as the motions of water along rivers, lakes, and groundwater, and to hindcast the rotation of fluids or to forecast the rotation of fluids that arises from planetary rotation and stratification. I experimentally discovered how to investigate the hydrodynamics and the magnetohydrodynamics of rotating fluids. The reason those problems were called grand challenges in supercomputing was that they were considered too computation intensive and therefore impossible to compute on existing supercomputers. I experimentally discovered how to make the impossible to solve. That is impossible within a vector processing supercomputer and make it possible to solve and possible across a new internet. That is a new ensemble of 65,536 tightly coupled processors that shared nothing between each other and that defines a new supercomputer. I experimentally discovered how to make the impossible to compute possible to compute, and how to execute the fastest computations by experimentally reducing the time to solution and reducing that time from 65,536 days of computing or 108 years of computing on one processor or one computer to only 1 day of the fastest computing across a new global network of 65,536 tightly coupled processors or across as many computers. I experimentally discovered that new global network as a parallel processing machine that is not a supercomputer per se, but that is a new internet de facto. In an echoic retentive manner of speaking, I experimentally discovered 108 years in 1 day, and I discovered a new supercomputer that has a better cost-benefit ratio. I'm Philip Emeagwali. My technological quest was to invent new ways to increase the speeds of computers and ultimately to invent the fastest supercomputer. The supercomputer of today will be the computer of tomorrow. We create tomorrow by what we invent today. Since 1989, school children doing school reports on the contributions of Philip Emeagwali to the development of the supercomputer often asked, "Where is Philip Emeagwali?" I was in supercomputer centers across the United States. I began supercomputing on June 20, 1974 at age 19. I began supercomputing in the Computer Center at 1800 Southwest Campus Way, Corvallis, Oregon, United States. I began supercomputing when President Richard Nixon was in the White House. However, my experimental discovery of how to parallel process and how to do so across my new internet That is a new global network of 64 binary thousand tightly coupled processors that were already available in the market, and how to fast compute, and how to communicate synchronously while computing simultaneously, and how to do both across a new massively parallel processing supercomputer made the news headlines in 1989. I made the news headlines 16 years after I began supercomputing in Corvallis, Oregon, United States. In the 1980s, I used my fingers to count the number of part-time programmers of the handful of massively parallel processing machines that existed. In the 1980s, I was the only full-time programmer of the most massively parallel processing supercomputer in the world, and I was de facto the first supercomputer scientist. As a lone wolf high-performance supercomputer programmer, I learned that it takes time to make an invention, such as inventing the fastest supercomputer. I failed 100 times before I invented how to harness the slowest 65,536 processors in the world, and how to harness those processors, and how to do so with a one-to-one correspondence between processors and problems. I invented how to harness those tightly coupled central processing units, or CPUs, and how to use them to simultaneously solve as many initial boundary value problems arising in extreme scale computational physics. I invented how to solve the toughest problems in computational mathematics and how to solve those problems across processors that shared nothing between each other, and solve them faster than any supercomputer that only vector processed its floating point arithmetical computations, or across processors that shared everything between each other. My supercomputing quest for the experimental discovery of the fastest parallel processing supercomputer began on June 20, 1974, in Corvallis, Oregon, United States. My quest for the fastest supercomputer began like the dispersal of the small seed of the 160-foot tall Iroko tree. The Iroko tree is venerated in my ancestral Igbo land of the southeastern region of Nigeria, of tropical West Africa. The small seeds of the Iroko tree are dispersed by bats. The bat unwillingly chooses what spot to grow. The bat unwittingly chooses what spot to grow the Iroko tree and choose the destiny of the Iroko tree. Like the Iroko tree, my experimental discovery of the massively parallel processing supercomputer seemed to choose where it will reveal itself. That experimental discovery gradually revealed itself across 16 years and revealed itself across 16 supercomputers and revealed itself across 16 cities. My quest for the parallel processing supercomputer began as a vague idea My quest for the high-performance supercomputer began as the small seed of an iroko tree. My quest for the parallel processing supercomputer began on a sequential processing supercomputer in Corvallis, Oregon, United States. In my first year of programming sequential processing supercomputers, I accessed those supercomputers via a teletype Model 33 ASR. The acronym ASR stands for Automatic Send Receive. On June 20, 1974, the teletype Model 33 ASR that I was using could be in my one-room studio apartment at 195A Knox Street South, Monmouth, Oregon, United States. But the teletype Model 33 ASR was inside a computer laboratory. That computer laboratory was at 345 Monmouth Avenue North in Monmouth, Oregon, United States. That computer laboratory was 22 miles away from the two supercomputers, both in the computer center in Corvallis, Oregon, United States, that I was remotely programming. The teletype Model 33 ASR automatically sent and received my supercomputer codes and data. My electronic messages were sent and received via telephone line. I used that telephone line to electronically speak with a programmed data processor that was called the PDP-8 mini computer. 9 months later, in late March 1975, I relocated from Monmouth, Oregon to Corvallis, Oregon, and I continued programming the supercomputer from 200 feet away and from a teletype Model 33 ASR that was in Kidder Hall at 2000 Southwest Campus Way, Corvallis, Oregon, United States. My experimental discovery of the massively parallel processing supercomputer revealed itself within a new internet that is a parallel processing machine that resided in Los Alamos, New Mexico, United States. That parallel processing machine is the iroko tree of my world of supercomputing. That parallel processing machine that I experimentally discovered to be a new internet that was powered by a new global network of 65,536 processors that were already available in the market was the precursor to the fastest modern supercomputer of today that is powered by a network of 10,649,600 processors that were already available in the market anyway. That parallel processing machine that I experimentally discovered is the precursor to the modern computer of today that is powered by about 100 processors that were already available in the market anyway. That parallel processing machine was the precursor to the high-performance supercomputer of today and the precursor to the modern computer of today. To invent is to create something out of nothing. For 16 years, onward of June 20, 1974, I, Philip Emeagwali, was the lone wolf supercomputer programmer that was perched on the top of that iroko tree of the forest of fastest supercomputers that are powered by billions upon billions of processors that were already available in the market anyway. In 1946, the programmable supercomputer was invented to compute automatically, to compute faster. For me, Philip Emeagwali, my technological quest was for the fastest supercomputer that I could program to make the impossible to solve problems arising in extreme scaled computational physics possible to solve, and possible across a new internet that is a new global network of 65,536 tightly coupled processors, with each processor operating its own operating system, and with each processor having its own dedicated memory that shared nothing between each other. That necessity to solve the most extreme scaled problems arising in computational physics took me to the crossroads of mathematics, physics, supercomputer, and internet sciences. During the 16 years onward of June 20, 1974, I sojourned from a system of equations of algebra that I solved on a sequential processing supercomputer to the crossroad between the laws of physics and the partial differential equations of calculus. I continued my sojourn to the crossroad between calculus and the system of equations of algebra. I continued my sojourn to the crossroad between algebra and a set of floating point operations of arithmetic. I continued my sojourn to the crossroad between arithmetic and my new global network of processors that is a new internet. I experimentally discovered that the processors are to the modern supercomputer what the elements are to the periodic table. I experimentally discovered that the processors are the basic building blocks of the modern supercomputer, just as atoms are the basic building blocks of molecules. I experimentally discovered that computational physics is at the foundation of the fastest supercomputer, just as axioms are at the foundation of axiomatic mathematics. I experimentally discovered that the regular short and equidistant email wires that I visualized as fiber optic wires of the Philip Emeagwali internet are its basic building blocks, just as the hypercube is constructed from the cube and is constructed from the regular and equidistant edges of the hypercube from lower dimensions. I visualized the new Philip Emeagwali internet as a small copy of the planetary-sized internet and as a new global network of 64 binary thousand tightly coupled already available processors that is de facto one seamless cohesive unit that is the fastest supercomputer that computed in parallel or computed by solving 64 binary thousand initial boundary value problems at once. My experimental discovery of the massively parallel processing supercomputer was independent of processor technology. That experimental discovery was a blueprint for a new internet that in turn is a prototype of the Philip Emeagwali cosmic supercomputer. I invented that cosmic supercomputer in the 1970s and 80s, and I describe it as a machine that can accurately be used to forecast the weather. The supercomputer is not fast enough to simulate the long-term changes in the Earth's atmosphere that is also known as global climate change. For the 4 decades onward of 1946, the sequential processing supercomputer, the sequential processing or vector processing supercomputer that was powered by only one isolated processor, that was not a member of an ensemble of processors, inspired the development of weather forecasts. Each weather forecast is computed from a supercomputer model that is rooted in a companion mathematical model that is rooted on the laws of physics. At the foundation of the supercomputer weather forecast is a large system of partial difference equations of algebra that was derived from finite difference discretizations and approximations of the primitive equations of meteorology. The primitive equations are a system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations that is the toughest problem in calculus. For those 4 decades, the weather forecast was generated within a supercomputer that computed with only one isolated processor that was not a member of an ensemble of processors. One of the reasons the weather forecast of today is more accurate than the weather forecast of the first 4 decades onward of 1946 is that today's weather forecast is simultaneously computed in parallel and synchronously communicated across up to 10 million tightly coupled already available processors that shared nothing between each other. My experimental discovery of the massively parallel processing supercomputer was independent of processor technology. That experimental discovery was a blueprint for a new internet that I envisioned as being a subset of the internet. I visualized that new internet as being at the core of an emergent cosmic brain. I experimentally discovered how to forecast the weather and do so with greater accuracy and do so across my new internet that is a global network of 65,536 tightly coupled processors. In my discovery, the weather is forecast by executing the set of floating point arithmetical operations that arises from solving the primitive equations of meteorology. The primitive equations is a system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern calculus. I discretized and replaced the primitive equations with my system of equations of extreme scale algebra that in turn approximated those partial differential equations. I discovered how to solve the arising system of equations of algebra that arose from the primitive equations of meteorology and calculus, and how to solve that extreme scale algebraic problem and solve it across my new internet, that is a new global network of 64 binary thousand tightly coupled processors. Those already available processors were identical to each other and were equal distances afar and apart from each other. That new global network of processors was a new internet. I discovered that new internet to be at the granite core of the high-performance supercomputer that I used to compute in parallel. In contrast to the new massively parallel processing supercomputer, the old sequential processing or the old vector processing supercomputer computed sequentially or solved only one problem at a time. I experimentally discovered how to more accurately forecast the weather and forecast it across the globe and across a new global network of tightly coupled processors that is a new internet. I programmed that new internet as a new global network of 2 raised to power 16 processors. I visualized that new internet as a global network of millions upon millions and billions upon billions of processors that had better cost-benefit ratio. That new supercomputer that I experimentally discovered is less expensive because its processors were mass-produced and were already available in the market. The reason my experimental discovery of the massively parallel processing supercomputer was reported in the news media and reported in the June 20, 1990 issue of the Wall Street Journal was that it was then a technological breakthrough to harness a new internet that is a new global network of 64 binary thousand processors. It was a technological breakthrough to experimentally discover how an ensemble of the slowest processors in the world could be harnessed and used to compute faster than any vector processing supercomputer that computed with the fastest processor. Back in 1989, the community of 25,000 vector processing supercomputer scientists in the world believed in Seymour Cray, the legendary pioneer of vector processing, who scorned and ridiculed the massively parallel processing supercomputer and dismissed the unorthodox technology as a huge waste of everybody's time. My experimental discovery of the massively parallel processing supercomputer that is a new internet enabled me to compress 180 years of time to solution on only one processor and to compress that time to just 1 day of time to solution across my new internet that is my global network of 64 binary thousand processors that computed in parallel. My technological breakthrough opened the path to the massively parallel processing supercomputer. That new path was taken by Chinese supercomputer scientists and used to compress their 30,000 years or 10,649,600 days of their time to solution on one processor to just 1 day of time to solution across 10,649,600 processors that computed in parallel. 3 decades later, China is exploiting the rich and the fertile consequences that arose from my experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July 1989 in Los Alamos, New Mexico, United States. For the past 3 decades, the world's fastest supercomputer was massively parallel processing, and do so either in Japan or in the United States. China now has the world's fastest supercomputer that is massively parallel processing across 10.65 million already available tightly coupled processors. Chinese high-performance supercomputer scientists divides computation-intensive problems in extreme-scale computational physics to enable them to solve them in parallel and as 10.65 million problems. China's use of 10.65 million processors to power its world's fastest supercomputers vindicated my use of 64 binary 1000 processors to record the world's fastest computation that I recorded on the 4th of July 1989. Parallel processing is the bridge that closed the distance between yesterday's sequential processing supercomputer and today's high-performance supercomputer. The massively parallel processing supercomputer is used to reduce times to solution and used to increase productivity and used to radically reduce times to market. The massively parallel processing supercomputer is used to tackle the toughest problems arising in computational physics, arising in modern calculus, and arising in extreme-scale algebra. I foresee our children's children massively parallel processing across their internet that will be their global network of 1 trillion processors that enshroud the earth. I foresee the internet of our children's children as their planetary supercomputer that solves our as yet unsolved grand challenge problems. Thank you very much. I'm Philip Emeagwali. Thank you.
Insightful and brilliant lecture. Insightful and brilliant lecture.